I'm really delighted to be here. As Martha said, I'm primarily a machine learning researcher, but I'm really interested in how we can use reinforcement learning to try to make people's lives better. And so I'm going to talk to you about some of the motivations and just sort of short vignettes of some of the types of work that we're doing. So one of the things that I think about a lot, and probably many of you think about a lot, is the number of jobs that people are having in this day and age. I think it's very different than, a couple of generations ago where maybe we spent most of our time at one particular company. I have a skewed view being in Silicon Valley, but it seems like people are changing jobs about every 18 months. It's happening all the time. And so I think when we think about this and we think of the new job opportunities that are coming up, both with automation and new challenges, we're going to need to do a lot of skills retraining and education throughout our lives. And so a lot of the work that I think about is how are we going to make sort of all these tutoring systems to help us learn things really quickly for skills that we haven't even thought about trying to master yet and things that will be coming up in the future. And I think that when we look to the past, we've seen some really incredible results for intelligent tutoring systems. So we've seen things like the ability to sort of double learning outcomes. I used to be on faculty at Carnegie Mellon University, and they've had some really incredible results on cognitive tutors and blended learning and ways to help people learn substantially more in the same time. But one of the things that's a challenge with this is that these types of results typically are incredibly resource intensive. So they will involve, 3 professors, 4 curriculum specialists, 3 years of, intense graduate student and additional staff support to make one product that then maybe works incredibly well, which is fantastic, but it's not clear we're going to be able to scale this up to all the things that we'd like to teach. So one of the things that I'm thinking about a lot is how do we take some of the insights of adaptivity and personalization and create systems that can provide similar, hopefully similar levels of benefits in a much more scalable manner so that we can sort of democratize these types of ideas and provide personalized adaptivity to many others. So one question you might think is, well, maybe we can just sort of provide better authoring tools. Maybe we can scale things up by providing teachers and other, perhaps non-PhD experts the ways to make these type of interesting adaptive systems. And there's been some really nice work on this, on sort of things like cognitive tutoring systems that help reduce this barrier, but it continues to be very challenging. And so one of the things that I'm going to be talking about today is sort of other approaches to this that we can actually think we might be able to scale to a much larger set of scenarios. And I'll divide it into 3 parts. So the first is going to be talking about if we do have data, if your platform is already going, how can we improve it? How can we enhance personalized learning without really human-intensive sort of analysis of those data trajectories and really diving into those data logs? How can we leverage machine learning to automatically improve existing educational technology? And then I'll talk more about these other aspects of how can we maybe sort of provide personalized learning support from the get-go, even before we launch a new product. So about 5 years ago, I was collaborating with my colleague Zoran Popovic up at University of Washington, and we were looking at the game Refraction. And Refraction has been played by around 500,000 students, and it's a game where students learn to split laser beams to fuel spaceships as a way to understand how fractions work. And one of the things we wanted to think about in this case is how do we organize the activities that the students are doing? So what is sort of the curriculum pathway people are going to go through? And you can imagine sort of adaptive pathways that might look something like this, which is based on some way they're playing the first particular level. We split. So maybe if they take over 30 seconds, then they get this particular activity next. If they take less than 30 seconds, they get this other one. And of course, that's a very simple sort of if-then rule, but we could have very complicated measures of how the student is engaging with this, because we get to see all of the click-through rates, and of course, we get to see not just how they worked on this particular activity, but all prior activities. So this is sort of a canonical example of how we would like to do personalization. And what we were interested in this case is how could we increase student persistence? This was an optional learning activity. It's online. And so unfortunately, there's many other competing things for students' attentions these days. And so the temptation to go from this to perhaps something else is quite high. And we wanted to think about how we could continue to keep people engaged. So while most of the students were receiving activities in a prescribed expert ordering, some students were not. We had the opportunity to have about 11,000 learners receive activities in random order. And what we could measure in this case is persistence, essentially how many levels do they complete until they exit the system, until they drop out. And so what our goal was is to learn what I call a policy, I'll say what that is in a second, to maximize student persistence, aka how many levels do they complete. Now what I mean when I say a policy is a decision policy, something that goes from that history of how the student is interacting with the platform so far to what is the next level to give them next. Now why is this a hard problem? This involves what-if reasoning. This is starting to be a really hot topic of machine learning right now, machine learning and artificial intelligence, but it has a huge intellectual background. At the courses, we can think of this as we have a series of students that are getting levels in different orders, and then we have some outcome variable. This could be test score, this could be how many levels they play, or some other objective that we'd like the system to be trying to maximize. And the question is, given this old data, how do we figure out what's going to be effective for a new student? Can we use that old data to better improve persistence for a new student? And there's two key challenges to this. The first is that the data is censored, which is you can never know how good your life could have been if you'd went and got coffee instead of coming to my talk. So sadly, that is a potential future that you will never realize. And similarly, in this case, we can never know what it would have been like if for this student they had received a different series of activities. We can't sort of reset our student and teach them fractions in a different way. So that's a fundamental hardness from sort of the technical side that we can only ever observe one outcome for each individual.
Excuse me.
Yeah.
Could you not look at the outcomes as they're doing something rather than the end outcome?
Oh, great question. Yes, so this outcome can be each outcome along the way, or it can be sort of a final measure. Yes, it works in both cases. So this can be a scenario where you actually have sort of intermediate rewards or intermediate signals, or where you only observe something after a whole sequence.
And if you did that, would you not be able to learn a lot more about their behavior and then adapt according to that rather than try and understand an outcome after many interactions?
Good question. So I think you're saying, well, could we actually, if we're seeing sort of, hey, the student is really struggling on this one, why should we wait all the way to the end to figure out what we should have done? Absolutely. So we can have algorithms that as they are making the decisions, they can react to how the student is performing, and then try to update from that information. If you're only looking at something like test score or something that is a delayed outcome, then we can't do that. But if you have things like after, how quickly can they complete each level? Those sort of things can be adapted to faster. That brings up, I'm not going to talk too much about it today, that brings up to me one of the really huge tensions and questions in using machine learning for education, which is what is the objective? Do we care about how quickly they complete a level? Do we care about what their test score is? Do we care about high school graduation rates? I probably care about employment, which is, employment and life happiness, which is a very, very delayed outcome. And so it's really hard for me to optimize what next level should you get if I care about your life happiness. So we typically work on things that are much more proximal, but that can be misleading sometimes. And in my world, we call that reward hacking. We call it where your system is optimizing for a reward which isn't really the outcome you care about. Okay, so one challenge is data being censored. Here's the other challenge, and this issue of data being censored comes up actually even if there's only a single decision you're going to make. This is commonly thought about in healthcare, treatment effect estimates for whether a new drug is better or worse to treat a patient. But when we're making not just one decision but a sequence of decisions, another big challenge is generalization in the sense that if you think about all the levels, let's say we have 40 levels and activities. If you think about how many different sequences you could have, there starts to be sort of this combinatorial explosion of I have 40 choices on the first time step and then 39 on the second. And we can't possibly test all of those. So we're going to need machine learning methods that can kind of generalize and say, well, if I tried A then B or B then A, can I use that to figure out what it would be like if I did A then A? So something to kind of generalize beyond the experience you've seen. So as I said, this is starting to be a very, there's a lot of interest right now in this, in the intersection of people who have classically thought about causal inference and counterfactual reasoning. There's a huge, wonderful history about this in things like epidemiology and biostatistics and econometrics. And now people like me in the machine learning community is also very, very interested in this. And let me just highlight for a second why this is particularly challenging when you're making a sequence of decisions. So I'll use a healthcare example from some colleagues of mine. Apologize to go out of education for a second, but I think it's illustrative. One of the challenges is if you want to teach people in a different way, by definition, that means you expect people to go through sort of a different sequence of knowledge states than what you have data about. So let me illustrate that with a healthcare example. Imagine that you have some way of treating patients and you want to consider a different way of treating patients, and you've got old data. And you want to use that old data to estimate how good this alternative decision policy would be. Well, so we start off and we have, let's say, maybe 100 people. And this is an intensive care unit example. So let's say, based on their current oxygen, your decision policy would say, let's do mechanical ventilation. Well, of the people, historically, who had this scenario, only some of them actually received mechanical ventilation. So now let's say you only have like maybe 30 people that actually got mechanical ventilation. And then you say, well, under my decision policy, I want to know what would happen if I applied sedation if they're under discomfort. Well, now again, a whole bunch of your data doesn't match that scenario. So now let's say you're down to like 20. So the challenge is that over time, if you are restricted to the data that you gathered in the past, only some of it is going to match the decision policy you're interested in evaluating to see how good that is. And so over time, the amount of data that is useful can greatly go down. So that's one of the big challenges here, is that even if you have a lot of data, most of it may be irrelevant for the new decision policy you're interested in. So I'm not going to talk about the technical ways that we tried to tackle this. I'm happy to talk about them offline. We used, in particular, methods that could allow us to get sort of an unbiased estimate of really how good we thought our new decision policy would be. So what we did in this case is we took our 11,000 learner trajectories and we tried a lot of different decision policies using that data set. And what we predicted was that we could find a new decision policy that would increase persistence by 30%. So that was just based on our old data. We're like, given our old data, that's what we think. Now, one of the things that was interesting about that is that we predicted, in fact, that the current expert policy was worse than random. So that was a little embarrassing for our experts, but it was a learning opportunity. And I think actually it was a nice illustration of how sometimes machine learning can be very helpful, because there are cases where we have really incredible educational theory to guide the pedagogical decisions we make. And then there are other places where maybe we don't know in this particular fractions game with these particular types of interactions what is the right ordering, and that sometimes our intuition can be wrong. But let me just highlight there that this is a prediction. So this is what our machine learning algorithm is telling us. Most people now know that machine learning algorithms are not always right. And so what we wanted to do is to test this. So what we did is we took another 2,000 learners, and we took the decision policy we'd learned from the past, and we ran a new experiment. And so we predicted that we would be 30% better. And in fact, we did. So in fact, it was 32%. So we found a policy that with our new 2,000 learners increased over random by 30%. We indeed verified that the expert policy was worse than random. And I think this was important for two reasons. One is that we actually improve student persistence, which is always exciting. And the second is that we have a method here that can kind of, predict the future, in the sense that it was a good estimate of how much better the system would be. It was a reliable estimate. And I think in many cases, there's quite a lot of overhead to changing our systems. It's not always possible to just change all the features of our systems very quickly. And so it's nice that we can sometimes estimate, if we were to do this change, how much of a benefit would it bring us? And that can inform whether or not we think it's worth it to make those changes. Okay, so that's sort of, we've done a lot of work actually on this. There's a lot of really interesting statistical questions around this, about how do we get the most out of a small amount of data. So the second question that I want to talk about, though, is what about if we don't have a lot of prior training materials? So I said before, one of my motivations is to think about, in our brave new world where we're going to have many, many jobs and we're going to need to do lots of lifelong retraining, how do we create these sort of tutoring systems? And it's really expensive and hard to make good curriculum. So I teach a reinforcement learning class here at Stanford, and I know from personal experience that getting assignments, making them completely full, there's no things that are ambiguous, they're very, very clear. It takes an enormous amount of time to do that. So how can we actually provide learning support with perhaps no training materials in the past? So one of the things that we were thinking about is that in many cases, such as crowd work and other scenarios, workers themselves are generating artifacts over time. So if I'm writing a product review, if I need a series of product reviews and I'm hiring a bunch of workers to do that, then the first workers are creating product reviews that maybe I could use as examples for later workers. And in general, often we have the case that, if I'm doing work, in some ways I'm providing a worked example. So this is sort of a similar idea to what's been called learner sourcing, which is you can take things that are created by learners to teach other learners. And what we're trying to think about here is that, let's imagine we're on like a crowdsourcing platform, where we've asked people to do a task. As people come in and do that task, can we use the things that people are making early on to teach people later? And if we can do that, which things should we use? Because not all of the things that people make are necessarily of equal pedagogical value. So as an example, we were looking at product reviews. Imagine that and this is a task that people really do. You can go onto many websites and see different things about product reviews, and what you can hire a bunch of workers to do that. And what we wanted to see is, could we sort of teach people to do better product reviews by looking at other people's product reviews in a way that we're sort of automatically creating a curriculum over time. So imagine that this is a particular one. There's a smoke alarm. You want people to compare between these smoke alarms in a way that is informative. And what we want to do is take these previous samples that were generated by past workers and use them to train future workers. So in this case, well, I'll give a little more background about how we did this. So what we did in this case is we had a series of workers coming in. They were asked to create product reviews about different products. And then we started trying to show those to people, show them to later workers. And the first thing that we found is that if we do that, you can't just show any of them to people. There's going to be a huge amount of variety in how well people can do this task. And if you just select any of the past examples to show a later worker, that doesn't necessarily help them learn. So if you show a really bad product review to someone who's about to do this task and you say, hey, I need you to do this task, by the way, here's a past example, it doesn't necessarily help them if it's very bad. But what we found is that if you provide high quality reviews, so if these have already been rated by an outside expert, and then you subsample those and only show people that are high quality reviews, then in those cases, you can actually improve the performance of later workers. So you can imagine this case sort of having a complex system where what you have is you issue a task, people start doing it, you get people to grade how well they've done it, the best solutions you feed back to use as training for later people as a way to sort of automatically start. Now, this doesn't deal with curriculum, but it starts to provide sort of intermediate training to people over time. Now, one thing that we found interesting is that high quality reviews improve performance, but not all high quality reviews were equal. So you might think that the best thing to do is to just give people whatever is the best example, whoever has done the best review so far. We didn't find that to be the case. We found that sometimes other reviews were more effective pedagogically. And I think that's an interesting tension, right? In the sense that it might be that some of these reviews are easier to sort of expose what are the features that are important to this task. And so that could create a tension of, do you ask people to create things that are going to help future people, or do you ask them to create things that are of immediate value? So I think that there's a lot of space here, but this is sort of an initial preliminary thought about how could we start to automatically create curriculum. And we've been doing other initiatives into this too, of things like how could we automatically create word problems from text to sort of have people practice factual knowledge and other. So that work has been focusing on using deep learning to try to sort of automatically create word problems. Okay. The final thing that's sort of related to this that I want to talk about is, well, what if we want to make this sort of personalized support, but we don't have any prior data? So I want to launch a new product, but I want to make sure that I can provide some level of personalization for the students from day one. And, but there's no prior data available. And I want to see if I can do this well. So in particular, we were interested in, can we create an adaptive algorithm that would sequence problems, so to lead people through a curriculum, given no prior data. And in particular, well, we could always probably do this. The question is whether it's any good. So we want to figure out whether this is better than what an expert would design. So typically right now, often, a teacher like in a class like me creates a hand-specified curriculum. And what I've said to you before from that first example about fractions is that if you have data, you can often do better than an expert. But now I'm trying to say, can we also do this even if we don't have any data? So we want to sort of go from scratch and see if we can do something better that might be able to help students learn. So in particular, we were thinking about the case where we might have a set of tagged pedagogical material. So this is Catchy, which is a game to help people learn sort of basic Korean language and vocabulary. And imagine that you have sort of a set of different activities for learning basic things about colors and shapes and numbers. And someone's tagged all the items for you. So you have what I'd call knowledge components or skills that are associated with each of this. And what we want to do is we want to take all of these materials and kind of adaptively sequence them for an individual in a way that should hopefully be better than an expert, but without prior data. So the idea in this case is that we're going to try to automatically organize this material based on those sort of tags or features into a graph. And once we have that graph, we're going to lead people through that graph. And that sort of progression through the graph can happen in a personalized way. So in particular, once you have these features, so if you have things that you can describe as like, green circles or 2 red triangles, then you can automatically create a graph that relates different sort of levels of concepts. So I could say, well, there are things that are green, there are things that are circles, there's the number 2, there's red, there's triangles. I could have red triangles, I could have green circles, I could have 2 green circles, 2 red triangles, or I could have the combination of all of this. So I'm going to assume in this case that I have items for each of these. And this just gives us a way to order them. It will give us a way to provide a graph over the items. And in this case, it's fairly simple, because essentially if one item is a strict superset of a previous item, we're going to consider it to be harder. It's going to be lower down in the graph. Now, clearly, for vocabulary learning, this is fairly straightforward. But I think for math as well, this is a pretty reasonable approach. That often you can describe things, am I doing 1-digit addition? Am I doing 1-digit addition with, a carry? So you can often think about creating similar graphs where you have this sort of way to express things as a finite set of attributes. Now, previous work by our co-authors had discussed how you could do this for a variety of different things, as long as you have some way to compare or some metric between the items to sort of give oneself a notion of ordering. So that allows us to create a graph from a set of items that were tagged. So this all happens automatically. And then the next question is, well, if you have this graph, how would you lead someone through it? So for this, we're going to use sort of a bandit-based machine learning approach, plus the idea of the zone of proximal development. So what we're going to assume in this case is that we'll start with people in sort of one of the root nodes, and then we're going to sort of slowly progress them through this.
Can you take a minute and describe bandit?
Sure, yes. So I'll explain that in just why don't I explain in a second after I talk about zone of proximal development. So in this case, we're going to assume that you have, in this case, we have it highlighted on the next one. Okay, not in this case, I just show you right there. So in this case, we're going to assume that we have some material that people have mastered so far, and then there are some nodes that are kind of on the outside of what people have mastered so far, following from the zone of proximal development idea. And what the idea is that you can move people to the next node that is kind of in their zone of proximal development. Multi-arm bandits are a subset of reinforcement learning which think about how do you adaptively figure out which things are most effective over time. What we're doing in this case is we will assume that there's sort of a set of material that is within someone's zone of proximal development, and we want to figure out which one to give to people. And what we use there as a signal is we look at basically derivative of learning progress. Did they start off not being able to get this item right, and now they're starting to get it right? And if you're having that derivative being positive, then we're giving that as a reward signal to an algorithm, the multi-arm bandit algorithm, that is used to adaptively select among the items, but only the items within the zone of proximal development. So this allows people to sort of iteratively, slowly move through this graph. And we keep track here. So in the green, you can see things that we're considering people to have mastered. The red is the things that people might not be ready for yet. And the green is things that are in the zone of proximal development, kind of the edge of the things that people, between the things people have mastered and the things we think they're not ready for yet. And this notion of looking at sort of derivative of learning progress, making sure that people are, something that people aren't learning well but are starting to learning well, that's the idea of keeping them in the zone of proximal development for that individual. That allows us to, even if we don't have prior data about the system, to lead people adaptively through it. Now, one thing I want to highlight here, I don't need to go into the math at this point, but we can't do this with no information or tuning. So there's a couple parameters that determine, that we have to set to determine how quickly people progress through this. But this is far, far less than what you would normally need to either specify by hand or that you would need to learn from previous data. Now, one other thing I want to highlight is, so this is the zone of proximal development. Particularly in vocabulary learning, we know that spaced repetition and forgetting is very important. So we combine this idea with a previous algorithm to keep track of when people might need to re-practice past items as a way to improve long-term learning. So what does this look like sort of as a whole path? We're going to start off, we have a whole bunch of different items. Each of them are labeled with different components like red triangle, 2, etc. Sometimes they're just things like red. We can automatically create this curriculum graph. Then we can lead people through it using this notion of zone of proximal development, and that will pick one of these items to display to the student. Now, I just want to highlight here that one thing that we ended up thinking about a lot in this case and ended up being really important was to decide what should this graph look like in terms of what level of granularity. So I think this is important in terms of it has big implications for whether or not personalization helps. So in this case, for this online learning game, we could think of each of these different items as being tagged with different levels of information. So if someone showed this to me, I could say, well, this is a color and shape object, or I could say it's a red triangle. Similarly here, I could say this is a shape and a shape, or it's a circle and a triangle. So there are different levels of granularity on which I can represent items. And the choice for this, which way I'm representing items in terms of what features, is going to change what my graph looks like. Because I said before, let me just go back to here. So in this case, this is looking at green being totally different than red. But if I only say these are both colors, then I would merge them together. So there's several different choices for how to represent things. And just how, if you want to demonstrate that you understand a particular grammatical rule, your teacher didn't make you demonstrate all possible instances of that in the English language. They said, well, if you could do it, for maybe 5 or 6 examples that I've given to you, you probably know the rule, and then therefore we expect you can generalize to all other cases. Similarly, once people figure out, when I explain color and shape, so I probably should explain the task here. Here you have the Korean characters, and you have to figure out which of these are relevant and in which order do they go. So once you figure out that I always put color before shape, or the other way around, if you can demonstrate that you can do that successfully a few times, I probably don't need to ask you about all combinations of all colors and all shapes to verify you know that structure. So what we ended up looking at here is sort of a more coarse structure where we could combine together color and shape and number and have a more compact graph. And that can give more opportunities for personalization. And in particular, it can give more opportunities for students that are going faster or perhaps have more prior knowledge to accelerate through the graph. So this is what it looked like in this case. So now we have this coarser graph. And that means once we select an item, as sort of a node in here, that actually corresponds to a whole set of items, all of which say are color and color or color and shape. And then we select among one of those to show to the student. So how do we define better in this case? This is also an optional learning activity, and so we don't have the opportunity to necessarily do post-tests. But one of the things that is interesting in this case is that the combinatorics start to get very large. So if I go back to this case, to explain this sentence and get that all in the right order and the right set of subsets from this, if you were to guess from random, I think it's around 1,000 options. So it's possible somebody could randomly guess this and get it right, but it's very unlikely. And so because of that, because a lot of these start to have very large combinatorics, we felt confident that if people were doing these correctly, that was an indication that they understood it. So that's not always the case. If we had a multiple choice test of 1 out of 3, I don't think we could trust that as well. But here, because it starts to be 1 out of 500 or 1 out of 1,000, and we only consider things as correct if they get it right on the first go, then it meant that we felt like we could more look at in-game performance. So one of the other interesting things about having these graphs is that if you get information that people can understand something that's further down, something that's more complicated, like color and shape, that can give you evidence that they understand prerequisites. So just like if I can do addition with carry operators, I probably understand addition. If I can do more complicated things further in the graph, then I can use that to sort of give me evidence or increase my belief that people have understood earlier topics. So I'm happy to talk more about the metrics offline. Let me say a little bit about what happens. So what we had here in this case, this is our new adaptive approach. We're normalizing everything to 1. We had a particular fixed progressions we considered. These were designed by experts. And then this is sort of how much people have completed. So again, we have this issue that people are dropping out over time. And we were looking at how quickly people could get to these levels. And what we found in this case is that people could generally, who are in the adaptive condition, could get to those levels significantly faster than people that were not in the adaptive condition. So people are sort of getting to they're able to learn the same amount much faster through this adaptivity, and significantly more, so about 1.2 to 1.4x faster to reach these later levels. Now this is a small amount of data, so this sort of shows for these different conditions over time. So some, how long did it take people to get to 10 steps, to 15, level 15, 20, 25, 30, and sort of how long did it take them to reach that in seconds. And it's significant at multiple levels so that we are able to teach people significantly faster. So that was really exciting because it suggested that by sort of doing something even without prior data, we were able to create an adaptive sequence for individuals that allowed people to significantly accelerate through the curriculum. So that was very exciting, but I want to point out a comment, well, to go back to my point about, what is the reward and what is the objective. So I want people to sort of, for learning to be efficient, engaging, and effective. And one of the things that we noticed in this case is that people learn faster, but they didn't learn more. Okay? So if we look at dropout, when do people drop out in terms of percent completed of the curriculum? These kind of look basically the same, right? Like there's really no difference, which means that we were helping people get to the same level of curriculum, but when things got really hard, everyone dropped out. Okay, so it meant that, if you're going to drop out anyway when it gets really hard, we can make that only take you half an hour of your time instead of, maybe 45 minutes. But then you still leave. And so I think it really speaks to that learning is very much a multi-objective. I know I'm putting on my machine learning hat, but it's a multi-objective discipline. And so we really want things that not only help people learn faster, but that they also learn more. So I think that this highlights why while this sort of adaptivity might be very helpful at accelerating learning, that there's other things that need to happen here to increase engagement or persistence. So I think just to summarize here, we've had other organizations be very interested in this before because they say often they're deploying new things and they really want to provide adaptivity and personalization, but they have no data and they don't know how to do this from day one. And so I think that sort of this notion of how do you automatically organize material, so assuming you have material that's tagged, which often we do, then you can use this sort of automatic graph construction to make a graph, and then you can automatically lead people through that. Can be sort of a nice way to bootstrap initial system performance. And then over time, one starts to get data that then one could use to make much more sophisticated forms of adaptivity. But I think this can allow us to provide personalization sort of kind of from day one of a new system when you're interested in kind of creating these adaptive learning pathways, particularly if you think there might be significant variability in the learners. So in some of our work, when we're looking at these sort of platforms for optional learning, we have a huge diversity of people that are coming to interact with these fractions games or these language learning games. And so these are exactly places where you'd like to be able to provide a lot of personalization to accommodate a lot of different backgrounds.
Emma, we have a question.
Why don't I just summarize and then we can do general questions. So just to summarize, I'm really interested in how we do sort of scalable personalization education at scale. I told you about some of the work that we've been doing to take, if you do have old data, how to use that to enable better personalized learning. How do we provide learning support if we don't have any prior training materials? And also, how can we start to provide support that maybe still be significantly better than expert performance in some cases when we have no prior data? Thanks.